Let's start this last talk of this parallel session. It's a pleasure for me to introduce Freek Witteveen from Amsterdam, who's going to present this very, very nice result, whose title is Classifying Unitary Dynamics with Approximate Light Cones in One Dimension, and with a subtitle, A Converse to Lieb-Robinson Bounds in One Dimension using Index Theory. All yours.
Thanks, David. Thanks for the nice introduction. Welcome, everyone. Very nice that you're all listening here at this great digital conference. I'm here to tell you about joint work with Daniel Ranard from Stanford and Michael Walter from Amsterdam. And indeed, the title is Classifying Unitary Dynamics with Approximate Light Cones in One Dimension. And you can find this also on the archive, and there it's titled A Converse to Lieb-Robinson Bounds in One Dimension using Index Theory, and there's a link in the Slack. So that's a lot of, it's a whole mouthful, this title, and I hope it will become very clear what this all means and what our goals are. So I'm going to start with a huge commonplace, namely the fact that local dynamics are important in quantum physics and computation. And of course, in the real world, locality is a very important concept. But also in quantum computation, there's often some notion of locality that's important. And let's just start with two very simple examples. So the first example is a quantum circuit. And here we see that this preserves locality. If I perturb it, if I look at this, it only acts locally. A second example is a translation operator, which just shifts a state to the right or the left by one side. And this clearly also preserves locality. So these are our two examples. And we now get a little quiz question for the audience. Can this translation operation that I described be implemented by some quantum circuits? And here, the quantum circuits I drew has two layers and it acts on two sides. But you could also imagine that it's a much deeper quantum circuit, or it acts on, it has unitaries that act on more sides. And yeah, think about this for a second. Maybe you have some intuition. So we'll get back to this later with the answer, of course. Another very important source of locality is in physics systems where we have Hamiltonians. So if we have some lattice and we look at a Hamiltonian on this lattice, and in this talk, I will actually focus completely on one-dimensional systems. So let's think of a one-dimensional system, a spin chain. Then a local Hamiltonian is just a Hamiltonian that can be written as a sum of terms that act only on some local patch. So for instance, a nearest neighbor Hamiltonian. And then we can look at time evolution along this Hamiltonian, e to the IHT, and we can wonder, is this a local dynamics? So the way to quantify this most easily is by looking at the Heisenberg picture, where we don't look at what happens with states, but with observables or operators, and then the time-evolved operator is just the conjugation by this unitary. And now the way to quantify this locality is by looking at some local operators supported at some set A, and thinking about how local is the time-evolved operator. So a very well-known fact, which probably most people in the audience actually know, are the so-called Lieb-Robinson bounds, which say that indeed there is some locality. So what happens is that there is a light cone of size v, velocity times the time t, and the time-evolved operator is almost supported within this light cone around A. So, but it's not exactly true. So to quantify this, we are going to look at commutators with other operators. And if we take an operator outside this light cone, if it was really sort of an exactly local map, then it would just commute with all operators. The time-evolved operator would just commute with all operators outside this light cone. But because it's not exactly local, we see that there is actually some, it doesn't exactly commute. So this is captured by the Lieb-Robinson bounds. So if we take some operator on an interval A, then we see that the time-evolved operator almost commutes up to exponential corrections depending on the distance to this other operator outside the light cone. So I hope this is either familiar or somewhat clear now. And this brings us to our next quiz question. Can a translation operator be locally generated? That is, can we implement it by some Hamiltonian evolution? And here I really want to allow very general time evolution. So maybe the Hamiltonian is also allowed to be time dependent. It doesn't have to be strictly local, but it can have some polynomial tails. It could even be such that there are no clear ways to simulate it using trotterization or something like that, as these assumptions break down. So that really is a bit more general question. And again, maybe you have some intuition. We'll see the answer later. So finally, I want to give another example of dynamics which are almost local and which do not come from some Hamiltonian in a physical system, just to give another nice example. And this is from a recent work on two-dimensional systems, which have something called many-body localization, which I will not explain, but the point is that in this case, there will be some dynamics on the boundary of the system. So this is again, the boundary is again a one-dimensional system. And this boundary dynamics does not have to come from a Hamiltonian. And in fact, the idea behind this is that actually these boundary dynamics, if they do not come from a Hamiltonian, this actually is some topological fact, and this tells you something about the topological phase of these systems. So this is another interesting example. Okay, so here's an overview of the examples we saw. We had some strictly local dynamics like these quantum circuits and translations, and we had approximately local dynamics, for instance, Hamiltonian evolutions, but also this slightly more exotic Floquet example. And I want to think of the circuit as being locally generated. It's all local unitaries, and also the Hamiltonian evolution is locally generated, but then there were these two other examples which were perhaps not locally generated. And in general, the goal of this talk will be to classify one-dimensional, approximately local dynamics. So I asked this particular question about whether the translation could be written as some Hamiltonian evolution, but I actually want to answer the very general question. When I have something that's approximately local, can it be written as some Hamiltonian evolution, or what are the other options? Okay, so in the strictly local case, there is a very nice formalization of this notion of local dynamics, and it's known as quantum cellular automata. And this is a definition that has taken some time to actually evolve to its current state. And the idea is that we take some lattice of quantum spin particles, and we will really think of this being a one-dimensional chain. And then we look again in the Heisenberg picture, and we look at some channel acting on these quantum spins, and we say that this is a quantum cellular automaton, or QCA from now on, with radius r. If it satisfies two conditions. So the first one is that alpha should be an automorphism, and this is sort of a difficult way to say that alpha should be a unitary channel. So just like before, it's just conjugating with some unitary. The reason we say automorphism is that this is a little bit more sensible for infinite systems. So for finite systems, it's really just a unitary channel. For infinite systems, there is this other formalism where it's more convenient to call it an automorphism. And secondly, we encode the locality in the following way. If we take some operator supported at any finite set A, then the image under alpha has to be supported on the set of sides within radius r of A. So this is illustrated in the picture on the right. And this notion has been very fruitful. On the one hand, it's useful to study quantum many-body dynamics, and there has been a lot of interesting work in this direction. And on the other hand, you could also use it as a model of computation, and there has also been quite some research in that direction. So this is a really fruitful field of investigation. And one very nice result is that in one dimension, QCAs are completely classified by something called the GNVW Index, after Gross, Nesme, Vogt, and Werner. And informally, we can think of this in the following way. We take our spin chain, we have our QCA, and we take some cuts somewhere in the spin chain, doesn't matter where, and then the index measures the number of qubits moving right if I apply this alpha, and the minus the number of qubits moving to the left if I apply alpha. This is illustrated in the figure. Okay, this is a very vague definition, of course. And let's have a look at some properties, which also uniquely define this index. And it turns out that the index is 0 if and only if alpha is some sort of circuit. And I think it's maybe quite intuitive that a circuit has index 0 in this interpretation, because there sort of goes as much to the right as to the left. But the converse is also true, and that's quite important. Secondly, the index of a translation is just given by the logarithm of the local Hilbert space dimension, which is also quite intuitive, I think, because here there's really a flow of qubits moving to the right. And thirdly, it has some other nice properties. For instance, it's additive under compositions and tensor products. As a consequence, this classifies one-dimensional QCAs in the sense that every one-dimensional QCA can be written as a composition of a product of translations and a circuit. So this completely classifies QCAs modulo circuits. And it also answers our first quiz question. And because the translation has a non-zero index and the circuits, every circuit has a 0 index, so they cannot be the same. And maybe this also corresponds to your intuition when you were thinking about it. Indeed, sort of there is this flow of information that cannot be captured by the circuits. So in our work, we actually give a slightly different definition, an alternative definition from the original one. And that is by, again, taking the spin chain and cutting it in two and looking at the choice states of the channel. So that means that we take 2 copies of our spin chain and we take a maximally entangled state between these 2 copies, and then we only apply the QCA to one of these copies. So it's illustrated in the figure here. And now the index is given by a difference of mutual informations. And here, for instance, the orange arrow captures sort of moving from the left to the right. And then indeed the mutual information between L prime and R, you should really think of as the number of qubits moving from the left to the right. So that really corresponds to this intuition that I gave. And one important fact about this index, which I didn't mention yet, is that it takes discrete values. So it's, for instance, if the chain is a chain of qubits, then it just takes integer values. And from this formula, it is of course not quite clear. What is nice is that this expression in principle also makes sense for approximately local dynamics. There, I don't need to use strict locality to define this. But it's not at all clear that this index would still take these discrete values, and perhaps it just breaks down if I allow some tails, or perhaps it breaks down if it does not break down if I allow exponential tails, but it does break down if I allow polynomial tails. And actually, it was also one of the open problems left by the original GNVW paper to investigate whether this index could be extended to approximately local dynamics. Maybe it's also a good point to comment on why is this actually called an index. Let's just really say that it means that it assigns some discrete value and it is stable under perturbations. And in fact, in the context of quantum walks, which this is a generalization of, there it really has the interpretation as the Fredholm index, and there is a whole field of mathematics dealing with index theory. And perhaps it's also related to our index, but we don't use any of that. So that would be interesting to investigate later. But we call it an index nevertheless. Okay, so now the idea is that we take the definition. To say something about approximately local dynamics, of course, we first have to define a bit more precisely what we mean with that. And the idea is that we take the definition of a QCA and we just replace this notion of strict locality by Lieb-Robinson type bounds. And here, that really means that there's no Hamiltonian that sort of causes these Lieb-Robinson bounds or something like that. It's just that we use the type of bounds that you get in the theorem as locality bounds. Also, there will be no time evolution, there will be no continuous parameter, there's just a single step dynamics. So, well, here's the definition. So we take some function that's decaying, and that will sort of bound the decay of our tail. So it could be exponential, it could be polynomial. And then we define an approximately locality preserving unitary, or an ALPU, with f of r tails on spin chain to be an automorphism, again, of the quasi-local algebra, to be precise. Doesn't matter if you don't know, which is such that if we take any operator supported on some interval, and if I take an operator which is supported at least r sides away, then they almost commute for large r, with this bound precisely being given by this function f of r. So the type of bound that you see here is very similar to the type of bound in the Lieb-Robinson bounds, except sort of some things are a little bit abstracted away. There's no Hamiltonian, no time evolution, and we allow very general functions for these tails. And in particular, Hamiltonian evolutions will give rise to ALPUs. Okay, so now our first result is that actually any ALPU can be approximated by QCAs. So if we have an ALPU with f of r tails, then there is a sequence alpha r of QCAs of radius 2r, such that if I look at any local operator on some finite set, the norm difference of alpha and alpha r applied to this operator goes to 0 as r goes to infinity, and it goes to 0 precisely as this function f of r that bounds the tails. So in other words, the alpha r converge strongly to alpha. And you can think of this a little bit as in quantum simulation of Hamiltonian evolution, where you also have an approximately local dynamics, namely the Hamiltonian evolution, and you want to approximate it by a quantum circuit, which is a QCA. So that's a special case, but in this case, we don't have any Hamiltonian, so we cannot do trotterization, but we just have these Lieb-Robinson type bounds that we have to work with. So, so the proof will be quite different, but morally, it's very much this idea. And once we have this, we can actually use this to define the index for ALPUs. So it turns out that the index, if we take the sequence of approximations, alpha r, then for large r, the value of the index of alpha r just takes one fixed value, and that's independent of the choice of approximation. And thus we just define the index of alpha to be this stabilizing value of the index of these approximations. And okay, this is maybe not the nicest definition, but it actually turns out that if f of r decays faster than 1 over r, which is a pretty weak condition, I would say, then the index is really, again, given by this difference of mutual informations as described before. But now we know that it's discrete, because this previous definition that clearly takes discrete values, because it's just the index of QCAs. Of course, this would not be super helpful if this index didn't still have nice properties, and unfortunately it does. So it still has the same nice properties with respect to composition and tensor products. And also, and this is a very important property, if we have two ALPUs, then they have the same index if and only if they are connected by a path that goes through the space of ALPUs with some uniform bound on the tails. So there's a path that starts at alpha and it ends at beta. And every point on the path is an ALPU with G of R tails for some G of R. It's a bit abstract maybe, but it actually turns out that that we can make this path by evolving along some quasi-local Hamiltonian. So if alpha and beta have f of r tails, then we can take this path to be generated by a Hamiltonian H, a time-dependent Hamiltonian. And the terms in this Hamiltonian will not be strictly local, but they will, you can write it as a sum over terms which are supported on some site on some set X, and these sets X can be arbitrarily large, but then the norm of the Hamiltonian of these terms is small. It becomes smaller with the diameter of these sets X, and the decay more or less goes like precisely the tail bounds. So in particular, we now also see an answer to the second quiz question. A translation operator can never be written as some Hamiltonian evolution, because again, the translation operator has a non-zero index, whereas every Hamiltonian evolution by point 2 will be connected by some evolution to the identity operation and thus has index 0. So we now see that this is not true for a very, very general class of Hamiltonians. And also, if we just replace the notion of QCA by ALPU and look at this GNVW index, then we see that all the important properties generalize, and the only thing that really changes is that the role that's played by circuits in the context of QCAs is now played by these quasi-local Hamiltonian evolutions. So that means that we have essentially classified ALPUs modulo these Hamiltonian evolutions. Okay, finally, I want to say a little bit about some of our proof techniques. So there's a notion of a near inclusion of algebras, and say that we have two algebras on a Hilbert space. Then we say that A is epsilon included in B if for every operator in A, there is some operator in B nearby, as in the formula here. So there is a nice theorem from 1980 by Christensen, which says that if we have two algebras A and B, and they could be infinite dimensional as long as they're hyperfinite von Neumann algebras, which form an epsilon inclusion for sufficiently small epsilon, then there exists a unitary that rotates A into B, and the norm difference of U to the identity is actually small, and this is and completely dimension independent. So it's a very nice result. If you've ever heard of it, you can think of this as a type of Ulam stability, which is well known in the context of groups, but now for general von Neumann algebras. And we give a self-contained proof of this in our appendix if you're interested in this result. And we also prove some additional properties of U. Now, the idea how to use it is that we take our ALPU with f of r tails, and then first we block sides so that alpha is nearest neighbor up to some small error given by f of r, and the number of sides we block is r. And then we apply this theorem to find a couple of rotations that we apply to a sequence of half-chain algebras. So all the algebra of all operators supported on, say, the left half or the right half side of the chain. And this gives us a recipe to find an alpha n, which is strictly local around sides 2n and 2n plus 1, and which is close to the original alpha. And now there is a nice result by the original GNVW paper, actually, which shows that if we have this strict locality, locally even, then there is a nice tensor factorization property. So the algebra at sides 2n and 2n plus 1, it splits into a left moving part and a right moving part, really as a tensor product. And this then allows us to, when we construct this alpha n for all n, we can glue them together to a single QCA. And that will be the approximating QCA. So this is a very rough sketch of the proof. If you're interested, of course, I'm very happy to tell you more. Finally, a short outlook. So our approach works for an infinite chain, and it also works if you have an open chain. But in that case, the index is always 0, so it's perhaps a little less relevant, but it doesn't work for the periodic chain yet. And that really is a sort of an artifact of our proof, I think, because there is no nice left-right factorization, and we really hope to also extend this. Then there has been a lot of very interesting work recently, the last couple of years, on the classification of higher dimensional QCAs. and there is a full classification in 2 dimensions, which is very similar to the 1-dimensional classification. There are actually some exotic examples in 3D, so that's intriguing. And we really would like to find out what is the deal with ALPUs in higher dimensions. So can we also find these approximating sequences of QCAs for higher dimensional ALPUs? And our proof techniques are quite specific for 1-dimensional systems. So maybe we have to think of something completely new. Maybe we can use this classification in 2D. We'll see. And another direction for generalization is noisy QCAs. So instead of relaxing the locality assumption, you can also relax the unitarity assumption. And perhaps if you have almost unitary, strictly local channels, then they are close to a QCA. So that could also be another interesting question. And finally, we had this nice algebra stability result from the 1980s that we discussed. And we're also intrigued by this result and wondering whether there are any other interesting quantum information applications for this type of result. And hopefully here at QIP, there are so many experts in all kinds of QI applications. So I'm curious to hear if you have any ideas. Okay, I'm looking forward to questions and discussion, and thank you for your attention.
Thank you very much, Freek, for this very, very nice talk. Okay, there is one question on Slack which generated some discussion. So the question is, when you said that it doesn't matter where one makes the cut in order to define this index, and then the question was if there was some translational invariance assumed, and then, okay, one of your co-authors answered that indeed no, but maybe you could provide some intuition. Why not? I mean, there were some comments about flow of information, conserved quantities, but maybe, I mean, you can just comment yourself, maybe.
Yeah, sure. I mean, it's a very, very good question to ask, I think. Yeah, I can say something about the, so the answer is perhaps a little bit technical, but if we go back to this picture with this factorization, so what happens is that at each side, we see that sort of the algebra factorizes in a left moving part and a right moving part. But now by looking at this on consecutive sides, you see that the dimensions will have to match in some way. And they will have to match in such a way that, that this flow of information is indeed an invariance. So this is something that was, of course, shown in the original paper already, and I think it's not quite intuitive when you first see it from the definition, but yes.
Okay, thank you very much, and I think we should probably move the rest of the discussion to the roundtable. Let me just comment that there is now a plenary, I mean 1 minute, a plenary talk in the main stage. It's a short plenary talk. It's just half an hour. In some versions of the program, it says that it's 1 hour, but it's half an hour. And then the roundtables for this session, for the 3 talks, will be after that. So at 10:30. And okay, there is there you can. I mean, there are 3 roundtables, one per speaker. I mean, just please select both speakers and interested people the right one. Now, okay, I think we finish here, and then I ask everyone interested to move to the main stage for the plenary.